All right. Good morning, everybody. I hope everybody's doing well. Welcome to Wednesday. It is the middle of the week. A couple things I want to mention here before we get too far in is just a reminder: the Integration B study guide is up, and it will be there until the Integration B. Signups are due by this Sunday, so if you're interested in participating, please do. All the information is found in both of the links that you see on your screen right here. The other thing I want to talk about is, let's see, we have a quiz today, 11.6. I'm not 100% sure. Let's see, quiz 11.6 settings. Let's see what the 12 minutes, one question. There we go. 12 minutes, one question. And let's see, other things I need to mention. 11.6 is like the entertaining one, right? It's ratio test and root test. The other thing I want to mention is that if you scroll down to unit 3 here, let me get in the student view so you see the same view that I see. If you scroll down to unit 3 material, you can see the unit or the section that we're in, representations of functions as power series. I have already filled in a lot of the video information. So we have the first 2 lectures on it from last Friday and then this Monday. And then we'll have the last 15 minutes I'll put in to after we're done with lecture today. So that'll finish out 11.9. Also, there's some things that are just online content. So I made videos for all of that. That online content can be seen in the lecture notes. So if you open up the lecture notes, you'll be able to see that. Well, all the stuff we talk about it, but there's certain parts of the online lecture notes that say online content. And that's where I just reserve time on for a video lecture online that I post in here. So you can see that, what is that? Example 4, number 4 from 11.9. You'll see it right here. Example 11.9, number 4. Also, that little process that I created last time, I made videos for. So I started with the ladder view of calculus, which just means how I view calculus as far as integration going up a ladder, differentiation going down a ladder, and talking about how when you differentiate, you can remove parts of domains. You can also remove edges from intervals of convergence. And when you integrate, you can actually gain parts to a domain, and you can also gain edges on your interval of convergence. So I mentioned that in this ladder view of calculus video, not terribly long video. I think it's pretty short. It doesn't say on there, but it might be maybe 12 minutes or something like that. And then the game of power series. That video right there is the one that the process that I kind of created on the fly in class last time. And so I'll be using that process for a couple examples today to remind you. So anyway, you can see all the videos are up there ready to go. So you're welcome to watch them whenever. And now, without further ado, we shall go into lecture. All right. Let me do one thing here. I want to mute my screen. All right. Going into lecture for today, we're going to round out section 11.9. Let's see. I can see some blank pages on here. So let me just find out exactly where we are. Okay. So that was the very first page. And by the way, I recopied my lecture notes over. So there are going to be some duplicates of pages here. So forgive me while I power through this really quickly. I'm not going to describe anything. I'm just going to find out where we were. You'll see a blank page every now and again like this, but we already had done that. I just did it on a different page. That's all. So let me keep going. It's my online video, the calculus of power series. We're getting close to where we left off. Let me actually zoom out on this too. So this is where we started talking about function world versus power series world. That was kind of exciting for me. That was kind of neat. And then here's where we continue to do that. Now, this is where we're going to pick up. So where we left off last time, we had proved that the natural log of 1 plus x is equal to this summation right here. And we also mentioned that the interval of convergence is -1 to 1, open interval of convergence. So interval of convergence on this is -1 to 1. In the long run, I'll probably gather up all of the identities that we create. What page is this? 14. So let me go all the way down to the bottom here. And what I'll do is I'll create a new page. And we'll go ahead and start writing down all the little identities that we create as we move through this material. So we have not proved it yet, but we have seen that oops, I'm way zoomed in. Let me zoom out a little bit. We know that e to the x, we'll prove it. Actually, I've already proven it in a future video. So I'll show you where to find that. But the e to the x is a summation n equals 0 to infinity of x to the nth power over n factorial. That was one of the identities. That's kind of the initial function we started playing with. Just to let you know, we haven't proven that equality is true yet, but I do in an online content video in chapter or section 1110. So just to let you know, that does get proven very quickly in the interval of convergence. So maybe I should do, well, I'll just do interval of convergence. It converges on -infinity to infinity. So in other words, as long as you expand out an infinite number of terms to this polynomial expansion on the right-hand side, it will identically give you e to the x. So if you want to know what e to the 30.2 power is, you would plug 30.2 into this polynomial expansion, and it would give you the exact value. And by the way, that's how calculators do it. So it's not that the calculator has e to the x in it. It has there's an algorithm to create the polynomial expansion. So anyhow, and then last time we proved the following: the natural log of 1 plus x is equal to, I have to kind of cheat. This is the one I never memorize, so I'm just looking over to my right, equal to the summation 1 to infinity of -1 to the n minus first power, x to the nth over n, and its interval of convergence is -1 to 1. All right, so those are two that we've dealt with. So let me go ahead and hop back. That we were on page 14. So let me get to page 14. I think, yeah. So we had proven that last time. So let's go ahead and use that. I'd like to use these as we prove them. So here we go. We've got find a power series representation for the function and determine the radius of convergence. And just for our sake here, I'm going to remind us right now the natural log of, again, 1 plus x, because it's so new, it's easy to forget, is the power series version of it is the summation n equals 1 to infinity of -1 to the n minus 1, x to the n over n. All right. And its interval of convergence as written is -1 to 1. Probably a better way to say that for right now is that the absolute value of whatever picture we're dealing with has to be less than 1. That's actually probably a safer way of writing that. So we want to find a power series for this f of x equals natural log of 1 minus x to the 9th over x. From this point forward, as you're looking at functions and you're asked to create a power series for that function, you really need to think about, do I have a representation for the base function itself? That is for natural log itself. And you do. You have this representation right here, natural log of 1 plus a picture. We don't have 1 plus a picture. We have 1 minus a picture. But if I build that table that I was doing earlier in last lecture, I had a function world. And then I had a power series world. And I said, draw 3 rows. Well, in this case, you don't actually need all three rows because you have a direct link between your function f, which is the natural log of 1 minus x to the ninth over x. You have a natural or a link between that, and over to the right, let me go ahead and just do this. I'll start here, start. And I want to end with its power series representation. So I want to end over here with its power series. Okay. And remember last time when we created this method, we said, oh, well, you can drive up, over, and down. That's one way to do that. So you can integrate our function f and then maybe find a power series for that integral and then take the derivative to end back at the power series representation of f. Or you could differentiate your function, find its power series, and integrate the power series to get back to the end, right? So there are two directions there. But then there was a direction I had mentioned last time, which is straight across. And I said, normally you would not be able to do that. It would be a simple question if you were able to do that. Well, here's a case where you can do that because we have a representation for the natural log of 1 plus a picture. And so we could rewrite this natural log of 1 minus x to the ninth as the natural log of 1 plus a negative x to the ninth all over x. And that is the same as, so let me go ahead and draw my little driving link over here. That's the same as 1 over x, I'm just factoring off this denominator, that's all, times the summation n equals 1 to infinity. And now I will look at my identity right here that we proved last time. It's going to be negative 1 to the n minus first power times whatever this picture is that we're adding. And the picture that we're adding is a negative x to the ninth. So times a negative x to the ninth raised to the nth power. And that's all over n itself. Now all you need to do is actually just clean that up. So notice this is a rare case where you start at your beginning, your start right here, and you had the option, obviously, of taking the integral of f if you wanted to. That would be a pain, though. You can see the integral, that would be just terrible. Or you could have taken the derivative of f. Again, that probably would have been a pain. But you could have driven north, east, then south to get at that result, possibly, or south, east, and north to get to that result. But again, because we have a cool little identity above that we've already proven, we can actually drive there directly. So let's go ahead and clean up this power series. It's pretty much done, but this is not how you would answer. So let me use the space down below, and I'm just going to point an arrow so that I have a nice clean space to work with. I'm going to showcase that this is 1 over x summation n equals 1 to infinity of the negative 1 to the n minus first power. And then we have a negative to the nth. So a negative 1 to the nth. I'll just go ahead and do that. And an x to the ninth to the nth, which is x to the 9n, all over n. Slowly cleaning this up. And you could see negative 1 to the n minus 1 times negative 1 to the n. Those powers, those exponents, will add when you glue those two together. And also, I'm going to bring in this power of x into the denominator. And I'm almost done. I'm just taking my time to showcase my thought process. So this is a negative 1 to the 2n minus 1, x to the 9n all over xn. And now This is x to the first downstairs. I can go ahead and cancel a power of x in the numerator. So it's x to the 9n minus 1. And we're almost done. I just want to mention one more thing before we say we are done. I'm not going to put the -1 there. I'm just going to write x to the 9n minus 1 over n, and we're going to have a discussion about that coefficient. The discussion goes like this. This exponent, odd or even? Always odd. Yeah, very good. Always, always, always odd. And a negative number to an odd power is always negative. So this is one of those weird cases where it compresses down very quickly to just negative. So keep an eye out for that. It doesn't happen all the time. Just keep an eye out for it. Okay. So there you go. That is the power series representation of that function up there, which is, give it a moment for my screen to catch up, the natural log of 1 minus x to the 9th over x. Really a very beautiful power series representation. Not too terrible to derive either. As long as you know this power series expansion right here, which is the summation n equals 1 to infinity. And by the way, if you look at a textbook, it might be written slightly differently. It might be written this way, the summation n equals 0 to infinity of -1 to the nth x to the n plus 1 over n plus 1. These are the same statements, so there's no biggie about that. The other thing I want to mention here is, remember, this will converge as long as the magnitude of x is less than 1. Strictly less than. So the magnitude of whatever we plugged into this power, I should use a highlighter. The magnitude of that has to be less than 1. So we happen to know, let me go ahead and just state this. Where's my ink? There we are. That we need the magnitude of negative x to the 9th to be less than 1. Obviously, that means x to the 9th has to be less than 1, which basically means x has to be less than 1 in magnitude again. So no big change there. Not a big change at all. The radius of convergence is still 1. Right? Because that's, you're centering at 0, and the furthest away you can get is 1 unit. So our radius of convergence is still 1. Pretty nice. Questions on that example? Anything that I can clarify for you? Anything that I can adjust or help you out with? I'm going to move my camera slightly because I keep looking over to my left. Vanity. Whenever you see yourself, you look at yourself. Start talking to yourself. That's terrible. Is this identity one to commit to memory? Great question. It's not one that I commit to memory, so I will say it's not one you should either. When we get to the end here, so let me go back to that page I was building. When we get to this end here, and I'll try to keep this page going as long as possible, I'll just highlight the ones that are very important to remember. Like this guy right here, incredibly important to remember. But the natural log one is not common enough to memorize. If you memorize it, good for you, but it's not common enough that you have to have it built into your brain. Okay. Good question. Now, let's go ahead and I want to go to 15 because that's where we just were at. And let's move forward then. Let's see. The next example was I did as an online example. So you'll see this entire discussion and proof online. You can see it looks kind of large, but it's actually not. I spent most of the video talking about that whole function world, power series world, and stuff like that. But the punchline is this. The power series for tan inverse, to wait for my screen to catch up. The power series for tangent inverse is -1 to the nth x to the 2n plus 1 over 2n plus 1. Now, this is actually a good one to memorize because a couple reasons. First of all, while this is a tangent inverse, let's just talk about the odd or even behavior of tangent. We know that tangent is odd, so it should make sense, actually, and you should know that tangent inverse is odd as well, actually. If you go to graph tangent inverse, it looks like this. It's an odd function. And so it should make sense that tangent inverse should just be an odd polynomial. It is. All its powers are odd. And I kind of did a little bit of a reveal a couple classes ago where I told you that the sign was negative 1 to the nth x to the 2n plus 1 over 2n plus 1 factorial. And if you don't remember that, that's fine because we're going to see that in a few moments. But anyway, trig functions, their power series are alternating series, and their powers on their variables, x's, are representative of the behavior of the trig series or trig function. So for example, tangent's odd, so it's tangent inverse. And so therefore, it is the sum of odd powered polynomial terms. Cosine is even, so technically cosine would be just something with a bunch of even powers. So that's a lot of work for me to erase that just to showcase this and then get rid of it. But if it were a cosine, you'd have even powers like that. So it's really kind of a neat idea that you can recreate the power series for a trig function somewhat logically. But I'm going to write this power series down in our list, my black ink before I forget, and then we're going to use it. And this power series is so important, I do think you should have it memorized. This is the tan inverse of x. It is equal to the summation n equals 0 to infinity. And I guess that's probably why some authors start the natural log at 0. It's because every other power series starts at 0, so why not, right? And it's going to be an alternating series, as all trig functions are going to be, just to let you know. So negative 1 to the nth. And then we have x to the 2n plus 1, because, well, tangent inverse is an odd function, over 2n plus 1. The interval of convergence on this is inclusive, negative 1 to 1. And by the way, if you watch the video on the proof of this power series, which is really a great reinforcement of that new method that we kind of created last class, you'll see that the problem started with the statement that this converges for x, the absolute value of x being less than 1. In other words, for x between negative 1 and 1, but not including the edge points. But at the end of the proof, we end up finding out, whoops, it should include the edge points. So that was a very, very nice accident, a happy accident. And Raj's asking, would the powers always be even to if we were dealing with the sine? No, sine is an odd function. So sine is an odd function, so powers would always be odd. Yeah. Cosine is the even function, so the powers would be even there. All right. So let's go ahead and use this tactic to deal with the next problem in line. Or I shouldn't say tactic. I should say use this theorem. That's a good way of saying that. So looking over here, give me a moment. There we go. Find a power series representation of the function to determine the radius of convergence. Well, I mean, what are you going to do? I mean, this is we just proved what the tangent inverse power series is. So if I were to draw that table down, which I'm not going to because we know what the power series expansion for tangent inverse is, but if I had drawn the table down, I'd have a row that had f here, and we would start, and we'd want to end up the power series over here, but it's a direct drive over because the reality is we know what the power series is now for tan inverse. So this is going to be x squared. The power series for tangent inverse is a summation n equals 0 to infinity, -1 to the nth. And then normally, I'm going to write it this way. It's whatever your argument is for your arctangent raised to the 2n plus 1 over 2n plus 1. Right? So this is a really nice way to think about it, that it's just the argument that you're plugging it in there. So I'm going to go ahead and replace that happy face with the argument. X squared summation n equals 0 to infinity, -1 to the nth. And then we have x cubed to 2n plus 1 all over 2n plus 1. And remember, laws of exponents, powers raised to powers will multiply. So that will be a power of 6n plus 3. Just taking my time here. Some people have already figured out where we're going to land, but x is 6n plus 3 all over 2n plus 1. And then bring in these two powers of x, and you'll be done. The power series representation of x squared times the arctangent of x cubed is the summation from 0 to infinity of -1 to the nth, x to the 6n plus 5 all over 2n plus 1. In the radius of convergence, by the way, we need that argument, that happy face, its absolute value has to be less than or equal to 1. Well, our argument is x cubed, which tells me the radius of convergence is 1. If you take the cube root of both sides, you get this, and that means the radius of convergence is equal to 1. It's centered at 0, and it goes 1 to the right and 1 to the left. So its radius of convergence is 1. The interval of convergence actually is still -1 to 1. Again, very powerful if you happen to know the power series expansion for one of those pieces that you're working with. This is wonderful if you're dealing with polynomials times a power series or function that has a power series you know. Questions on that bad boy right there. Do we state the interval of convergence and radius of convergence at the end of each problem? If requested, yes. So in the problem, it'll state like, oh, find the power series expansion. Hey, what's the radius of convergence? Right. And I would code the problems that way as well. It's always nice to kind of do that, right? Notice, by the way, because I think this can be a sticking point, that we had just finished section 11.8 power series, and I had mentioned that when you find a power series, or when you're given a power series, you have to check the edge points to see if the power series converges at those edge points, right? So you have this interval of convergence, but how do I guarantee that it converges at the ends? Well, turns out the end behavior for our power series doesn't change if you're not integrating or differentiating. Okay, so if you happen to know the power series representation for tangent inverse, which we do, we know the original power series representation for tangent inverse was that its radius of convergence was 1, and it included the interval of convergence, included the endpoints. Well, because we did not, when we were transforming this into a power series, because we did not integrate or differentiate, there was no chance for us to gain or lose edges on our intervals of convergence. So there was no need to recheck those edges. The edges will still be included. Okay. So if you know the power series expansion, it's as long as you're not integrating or differentiating, you're not going to lose edges. However, most cases you don't know the power series expansion. You have to create the power series, and that is where you do have to check edges. All right, that may sound weird, but you'll see it in problems where you have to check edges. Just generally speaking, if you start with a tangent inverse or e to the x, or what was the one we just did, natural log of 1 plus x, there's no need to check the edges, none whatsoever, because those are born of power series expansions we've already proven, and we know what the edges are. All right. Let me see if there's anything else in here. I don't think there is. Nope. That's online content. That's it. And then the next page actually is, sorry, I can see my screen is taking forever. The next page is what I did in a video lecture for the ladder view of calculus. And then I did another one for the new method, the game of power series that we talked about last time. Really a very, very cool way of viewing how to create a power series from a given function. All right, so that finishes out 11.9.